This presentation is about Carolina Bay deformations and irregularities. The Carolina Bays are shallow elliptical depressions along the east coast of the United States whose major axis points toward the Great Lakes. The bays have raised rims and they are found on sandy soil close to the water table. The size of the bays varies from about 100 meters to several kilometers in size. The Carolina Bays completely cover the landscape except for places where water has washed away evidence of their existence. The geometrical shape of the Carolina Bays resulted from the mechanism by which they were formed and by the geologic and topological environment where they were emplaced. The archetype shape of the Carolina Bays is elliptical, but the geometry can be deformed by wind and water erosion, by ground movement, and by bioturbation, which includes soil disturbance by plant roots, burrowing animals, and human activity such as farming, damming, logging, urban development, and drainage of wetlands. The Carolina Bays are not thermokarst. Some geologists have proposed that the Carolina Bays have a similar origin as thermokarst lakes. Karst depressions are formed by the solution of minerals or by melting of permafrost that produce sinkholes. However, thermokarst lakes do not have the regular elliptical structure of the Carolina Bays, and their alignment is toward lower terrain for drainage rather than to a common focal point. The regular shape and orientation of the Carolina Bays was what first attracted the attention of geologists. The Carolina Bays are enormous. Several block-long buildings can easily fit inside some of the bays. LiDAR, a laser imaging technology, enhances visualization of slight elevations in the terrain and provides excellent images of the bays. The Carolina Bays have been described as either oval or elliptical. Melton and Schreiber in 1933 and Prouty in 1952 characterized the bays as elliptical, but they did not perform a geometrical analysis to verify that the bays were mathematical ellipses. Before we can talk about deformations or irregularities of the Carolina Bays, it should be mentioned that well-preserved Carolina Bays are perfect ellipses with an average width-to-length ratio of 0.58 plus or minus 0.05. This corresponds to cones inclined at approximately 35 degrees. An ellipse with the same width-to-length ratio as the Carolina Bay fits the bay exactly after scaling and rotating the ellipse. This makes it possible to model the bays as mathematical conic sections and to use ballistic equations and power laws relating energy to crater size to derive their conditions of formation. The Carolina Bays have been preserved because the porous ground allows rain to pass quickly to underground aquifers where water flows without disturbing the surface features. Nebraska also has elliptical structures called rainwater basins with the same geometrical aspect ratio as the Carolina Bays. The Nebraska basins also point toward the Great Lakes, but their orientation is almost perpendicular to the Carolina Bays. The Nebraska rainwater basins are on terrain that is 600 to 700 meters above sea level. Many basins have been greatly degraded by wind and water erosion, but ellipses can be fitted for the basins that have maintained well-defined borders. The projections of the major axes of the Nebraska rainwater basins and the Carolina Bays intersect at Saginaw Bay in Michigan. The Nebraska rainwater basins have the same elliptical morphology as the Carolina Bays. The Nebraska basins occur on abandoned Platte River fluvial deposits. Unlike the Carolina Bays that can drain by subterranean aquifers toward the Atlantic Ocean, Nebraska's rugged terrain allows water to flow on the surface, and this has contributed to the destruction of the elliptical features. Most Nebraska rainwater basins smaller than 4 kilometers have been completely obliterated. It is impossible to measure accurately the width and length of the basins when large portions of the elliptical rims have been washed away or covered by wind-blown dust. The glacier ice impact hypothesis, published in 2017, proposed that the Carolina Bays and the Nebraska rainwater basins were made by secondary impacts of glacier ice ejected by a meteorite impact on the Laurentide ice sheet approximately 12,900 years ago. The impacts of the ejected ice chunks with energies of 13 kilotons to 3 megatons liquefied on consolidated ground, and the ice projectiles created conical cavities inclined at about 35 degrees that were remodeled into shallow elliptical bays by viscous relaxation. The extraterrestrial impact and the saturation bombardment by the glacier ice boulders caused an extinction event and a global winter. The date of the extraterrestrial impact is deduced from the disappearance of the North American megafauna and the onset of the Younger Dryas cooling event. The hypothesis that ice impacts could create conical cavities was tested with a physical model to evaluate impact conditions and viscous relaxation. A target was prepared with a mixture of pottery clay, sand, and water covered with a light layer of colored sand. A slingshot was used to fire ice projectiles toward the target. The experiments revealed that the overturned flanges around the conical impact cavities become the raised rims of the base, and that adjacent conical cavities become overlapping bays. The overlaps follow the geological principle of superposition, in which newer features cover older features. These images illustrate the way in which viscous relaxation decreases the depth of the conical craters. The experimental container is shaken to promote liquefaction and speed up viscous relaxation. During the formation of the Carolina bays, the seismic vibrations of nearby impacts would have speeded up viscous relaxation. In this image, Carolina bays completely cover the landscape near Branchville, South Carolina. These bays have poorly defined rims, and water channels flow through many bays. The degradation of the bays makes it difficult to see complete ellipses and to count the number of bays. Human activity is responsible for much of the erosion. This is a satellite image of the same area as the previous slide. We can see rough outlines of some of the biggest bays, but the small bays are completely obscured by a patchwork of farmed fields. Drainage of wetlands and yearly plowing of the soil since the land was settled by European farmers has gradually destroyed these Carolina bays. The bays near Mappsville, Virginia in the Delmarva Peninsula are circular rather than elliptical. 35 million years ago, a meteorite struck the Chesapeake Bay and created a tsunami that washed away the loose surface sand of the Delmarva Peninsula. The shallow depth of unconsolidated material can explain why the bays in Delmarva are circular. An elliptical Carolina bay with a major axis of 400 meters requires a layer of unconsolidated soil 140 meters deep to allow the formation of a conical cavity inclined at 35 degrees. Conical cavities cannot be made on solid ground. Ice projectiles impacting a hard layer disintegrate explosively and create hemispherical shockwaves and circular craters like those illustrated here. Many Carolina bays have a thicker rim on the southeast side. The raised rims of the Carolina bay correspond to overturned flaps around the crater. The thicker rims toward the distal end of the bays were formed by a plowing action in the direction in which the projectile was traveling. From the time that the bays were discovered, many geologists suggested that the Carolina bays were formed by wind and water processes because the bays did not have shock metamorphism, meteorite fragments, or other evidence of extraterrestrial impacts. Tests of the bays by Brooks and his colleagues using optically stimulated luminescence produced a wide range of dates. The authors concluded that the Carolina bays were created over thousands of years. The dates for Big Bay in South Carolina showed that the concentric sand rims representing previous shorelines became progressively younger toward the bay interior, and that a wind-blown sand sheet originating from the watery river on the west was moving over the bay 74,000 years ago and was later modified 33,000 and 29,000 years ago. This research was done before LiDAR images became widely available and before geometric analysis revealed that most Carolina bays are perfect ellipses. The Eolian Lacustrine hypothesis for the creation of Carolina bays claims that active shorelines and Eolian deposition shape the bays according to alternating warm and cool periods in the Earth's paleoclimate. However, this explanation cannot possibly apply to the Nebraska rainwater basins that have the same geometry as the Carolina bays, but are 600 to 700 meters above sea level on terrain that has not been close to any sea for 60 million years. The Eolian and Lacustrine origin of the Carolina bays was bolstered by Kaczorowski's 1977 thesis describing wind and water experiments that modified circular pools on sandy soil. Kaczorowski's experiments did not produce the elliptical geometry characteristic of Carolina bays, but his thesis has been widely referenced in publications proposing the terrestrial origin of the bays. In contrast to the wind and water experiments, oblique impacts on viscous ground naturally produced inclined conical cavities that become shallow elliptical conic sections through viscous relaxation. The geometrical relationship between cones and ellipses was well known to the ancient Greeks. Just on the basis of geometry, the elliptical Carolina bays are more likely to have originated from inclined conical craters than from variable wind and water currents. The Eolian and Lacustrine hypotheses have never explained the detailed physical mechanism by which wind and water currents could produce perfect ellipses either experimentally or in Nebraska and in the East Coast. Optically stimulated luminescence, or OSL, is a method for dating sedimentary layers. Radioactive isotopes of uranium, thorium, rubidium, and potassium that occur naturally in the soil produce ionizing radiation that causes electrons to become trapped in defects of buried quartz crystals. Exposure to sunlight or intense heat release the trapped electrons. Luminescence dating estimates the time since grains of quartz were last exposed to daylight by detecting their subsequent response to light of specific wavelengths. The problem with using OSL on the Carolina bays is that the bays were not created by sedimentary processes. The bays were produced by impacts that formed cavities on the liquefied ground. The stratigraphy of the bays was subsequently restored by viscous relaxation without exposing the subsurface to light. Thus, the OSL dates of the subsurface of the bays corresponds to the age of the terrain and not the date of bay formation. The subsurface of the Carolina bays appears undisturbed as contrasted with craters created by impacts on hard surfaces. This can be explained by the behavior of viscous targets after plastic deformation. A projectile at ballistic speed penetrates the viscous surface by parting the layers of the target during the excavation phase. Experiments have demonstrated that viscous relaxation partially reconstitutes the stratigraphy because hydrostatic pressure increases with depth and promotes faster laminar flow at the bottom of the cavity. The cavity is filled from the bottom up, but due to friction, the interior of the bay never rises to the original level of the surface. This LiDAR image shows Big Bay with more geographical context than illustrated by Brooks. From an impact perspective, what Brooks described as an Eolian sand sheet could be debris deposited by a tsunami from an impact on the watery river. Notice that the small bay at the top of the image, circled in red, is over the sand sheet. This means that the small bay was emplaced after the sand sheet. Big Bay and the companion bay below it are covered with the sand sheet. This means that the sand sheet came after Big Bay was formed. But if the sand sheet is Eolian, why wasn't the small bay covered with sand also? These features of the terrain can be explained by the following sequence. Two big ice boulders created Big Bay and its lower companion bay. Seconds later, another big boulder impacted the watery river. The splash from the impact created a tsunami that dredged the sandy deposits that had accumulated along the riverbank for 74,000 years. The sandy soil was carried inland by the tsunami for 6 kilometers, and a sand sheet was deposited on a portion of Big Bay and its companion bay. A few seconds later, a small ice boulder came down to create the small bay on top of the sand sheet. If the sand sheet had an Eolian origin, one would expect that there should be more sand sheets all along the river, but this 11-kilometer section of the watery river has the only sand sheet in the region. Another clue indicative of a tsunami is that this is the only stretch of the river where the banks do not have sandy deposits or Carolina bays within 3 to 5 kilometers of the river. Some bays are deformed when the terrain moves. This image shows a large bay that has been stretched by uneven ground movement toward the creek. The bay has a wavy water channel, which indicates that the portion of the bay closer to the creek is more saturated with water than the portion away from the creek. This causes the bay to deform in the direction of water flow. Large bays are more likely to deform than small bays because a small bay can be carried intact by a section of moving ground, whereas a large bay may straddle several sections of ground that move at different speeds and in different directions. Catfish Bay in South Carolina is another example of a bay that has been stretched by ground movement. The bay is in a trough that drains to the northwest into the Great PD River and to the southeast into the Little PD River. Consequently, the original elliptical shape of Catfish Bay has been stretched in both directions. Notice that the smaller bays on the rims of the trough have retained their elliptical shape. These non-elliptical Carolina bays are found close to the banks of the Savannah River. They are examples of bays that were distorted by the topography of the terrain when they were formed. The color gradient indicates elevations. The orchid color in the center corresponds to an elevation of 58 meters above sea level, and the green color toward the bottom corresponds to an elevation of 43 meters above sea level. All of these bays have a flattened shape toward higher terrain. The distorted bays have an elliptical end and a flattened end. The shape of the bays can be explained by noting that the flattened ends of the ellipses are adjacent to areas of higher elevation, and that mudslides could have changed the shapes of the bays. The elliptical end can be fitted with an ellipse because mathematically only 5 points are necessary to fit an ellipse to an elliptical curve. The experimental model can be used to confirm the mechanism of bay deformation. An elliptical impact cavity is modified when the terrain is inclined. The distortion of the bay is caused by soil flowing downhill after the formation of the conical cavity, but the soil flows faster on the uphill side due to the steeper gradient into the cavity. The resulting structure has an elliptical end and a flattened end similar to the bays near the Savannah River. Some Carolina bays appear to have multiple or concentric sand rims. Proponents of Eolian and Lacustrine mechanisms claim that the multiple rims are evidence of bay evolution over long periods of time. But it should be noted that these terrestrial mechanisms cannot explain how the overlapping bays are created or the reason why the bays have elliptical geometry with specific width-to-length ratios. Experiments that demonstrate the transformation of conical craters into shallow bays sometimes produce bays with double rims. This image shows an internal V-shaped double rim caused by uneven laminar flow during viscous relaxation. Such internal rims are created when the centripetal laminar mud flow that fills an impact cavity from the bottom up encounters resistance as the liquefaction of the soil decreases. The overlap of the bays corresponds to the sequence in which the bays were formed. The principle of superposition indicates that the small bay in the center was created first, followed by the large bay, and finally by the intermediate-sized bay. This presentation demonstrated that the Carolina bays are typically elliptical because they originated from inclined conical cavities. The deviations of the bays from the elliptical geometry can be explained by the characteristics of the terrain on which the conical cavities were emplaced, and also by the action of terrestrial mechanisms such as erosion. The clues presented by the terrain may be interpreted in different ways, and sometimes it is difficult to determine the mechanism that formed a specific feature. We have to keep in mind that the passage of the meteorite through the atmosphere ignited fires that produce a lot of smoke. Also, the vapor trails from the re-entry of the ejected ice boulders created black clouds that completely blocked the light of the sun. The impacts of the giant ice boulders that made the Carolina bays probably occurred in absolute darkness. The dates obtained for various Carolina Bay features by optically stimulated luminescence show ranges of thousands of years, but it is wrong to apply a dating technology intended for sedimentary processes to a landscape created overnight by violent impacts. Reliance on these OSL dates will continue to cast doubt on the impact origin of the Carolina bays, but the geometrical conic sections will eventually prove more convincing because they enhance our understanding of the mechanisms that form the landscape.